Good afternoon. This is lesson 6 of industrial instrumentation. In this lesson, we will cover the torque measurements. As you know, the torque is very important parameters, even though it is not exactly the process parameters, but it is also a parameters which is of paramount importance for most of the mechanical measuring systems, wherever there is a shaft, rotating shaft. So, there is a need to measure the torque developed in the shaft, because it is necessary to know that the optimal force up to which that shaft can withstand. So, it is necessary to measure the torque in the system, so torque in the shaft. So, for that reason, so we have to measure the torque in the shaft. So, there are various techniques of measuring the torque. Now, we will discuss in brief two techniques, and we will discuss the details, one of the most modern technique, and its signal conditioning circuitry, which are actually used in the in the industry. It contains the torque cell, data transmission by slip ring method. Torque cell means you will cover all the three different cells, and when the question of data transmission comes, it is basically the third type of torque cells which we will discuss, which is based on the strain gauges. So, it is concerned with the third type of torque cell or torque measurement techniques, and wireless data transmission. There is one is a slip ring method, then there is a wireless data transmission. This we will discuss in details. At the end of the lesson, the viewer will learn the different torque measurement techniques, details of strain gauge based torque measurement, torque cell data transmission. Now, you see the measurements, as I told you earlier, measurements of the applied torque is of fundamental importance in a rotating shaft. It will ensure that the design of the rotating element is adequate to prevent failure under shear stress, because you see it is a rotating shaft. So, always there will be some shear stress will be developed. So, we must know the what is the optimum shear stress which the shaft will withstand and before failure. So, for that reason, we have to measure the torque. Now, torque measurement is necessary to know the power transmitted by the rotating shaft also. These are the need of the torque measurement. There are three methods of measuring torque, and these are measuring the reaction force in cradle shaft bearing. This is the one of the method, or I should say the Prony brake method. Then we have this is basically cradle shaft bearing, and the second is the Prony brake method. And third is the measuring the strain produced in a rotating shaft due to applied torque. This is basically based on the strain gauges. The third one we will discuss in details. This one we will discuss, third one we will discuss in details. Now, reaction force in shaft bearing, you see the torque transmission through a shaft contains both power source and a power absorber. There must be a power source, it must be some motor through which the power is coming, and it is transmitted to some other, suppose some lathe machines or some other devices. So, that is a power absorber. Now, the torque is measured by cradling either the power source or the power absorber end of the shaft bearing, and then measuring the reaction force F and the arm length L. Now, the torque will be given by F into L. So, we must know F, and we have already L is fixed. So, we will know the L, measure the L, we will measure F, and this will give you the torque. Now, this you see, this is our cradle systems. You see here we have absorbers, and we have a source, and we have a cradle. You see here this length is L. So, if we know L, and if I know the force F, this is the force F, so I can measure the torque. This is one of the oldest method of measuring the torque, right. Now, Prony brake method is basically a rope is wound around the shaft, and one end of the rope being attached to a spring balance and the other end carrying a load of mass m, right. So, it looks like this, you see we have a spring balance here and a spring balance, then is a rotating, actually the this should be little thinner. So, it should be the wire is wound like this one, it is wound like this and it is coming like this. So, it is little bigger and mass m is installed in one end and the spring balance is installed in the other end. This spring balance is graduated, so it is moving on a scale, okay, like this one, as a conventional spring balance system, right. Now, if the measured force in the spring balance if F is B, then the effective force FEF exerted by the rope on the shaft is given by FEF, that means F subscript EFF equal to mg minus FSB, where FSB is the measured force, right. If the radius of the shaft is RSH and that of the rope is R subscript smaller, then the effective radius is R effective equal to R shaft plus R, radius of the shaft and radius of the rope. So, if it is there, then I can write the torque in the shaft will be given by T equal to FEFF into REFF, obviously it will be Newton meter, right. Now, one of the most convenient, because you see in all the previous cases, both the cases Plonivec and the Cadle systems, so we do not have the output is not electrical, it is a mechanical output. It is very difficult to convert that type of mechanical signal in the electrical domain, and in all in the instrumentation systems, so always we prefer the electrical signal because it can be transmitted easily, it can be converted to the current domain, it can be transmitted over long distance, it can be digitized, all those advantages there in the electrical system. So, always we prefer an electrical system where in instrument system where the output is electrical. In this case, in the measurement of the torque by the strain gauges, you see basically the 4 strain gauges are used, right. I will show the diagram just now. 4 strain gauges are used because if the torque is rotating, so there is some amount of shear stress on the torque. So, we will measure that shear stress and find the torque, right, and then we will put the strain gauges. There are 4 strain gauges, as you know 4 strain gauges is always necessary to make the temperature compensation as well as the large bridge output. So, it will be it is converted to the electrical domain. So, they will be connected to a Wheatstone bridge and we will get unbalanced voltage, that unbalanced voltage will be calibrated in terms of torque. So, basically whenever we are talking of the sensitivity and all these things, we please note that we are considering this torque cell as well as the assembly, entire Wheatstone bridge assembly. So, it is the torque cell Wheatstone bridge assembly we are talking about, not the torque cell only or the Wheatstone bridge alone, clear. Now, it is most common method used for torque measurement. As I told you, this is a very common method, it is widely accepted method of torque measurement and it does not disturb. This is the most important thing. This is this third point is most important. I think this point is very important. It does not disturb the measured system by introducing the friction torque in the same way as do the last 2 methods described, because you see the last 2 methods basically we are not getting the actual torque truly, if you look at, because we are introducing certain amount of torque, because we are entering certain amount of frictions. So, so it will introduce certain amount of torque. So, we are not getting exactly the value of the torque in that type of measurement systems, right. It converts to an electrical signal, it converts the torque to an electrical signal. It is similar to the load cells. We have studied the load cell. Load cell, it consists of a mechanical element. Usually, we have seen the load cells of the unit link column type load cell. We have seen the beam type load cells. In all these different cells, you will find that that we are using strain gauges. It is similar thing on the wall of the shaft. The strain gauges are to be installed. It is similar to the load cell. It consists of a mechanical element, usually a shaft with a circular cross section, and sensors, usually strain gauges. You see, this is our typical strain gauge. This is our typical torque, measurement systems. It is actually a shaft. We have taken a section of the shaft, so this should actually go like this one, a section of the shaft, and the 4 strain gauges are installed on a 45-degree helix, right. Actually, if I say it will look like this, if I take a blank page, you see here, actually this, if I take the shaft like this one, these strain gauges are installed on a 45-degree helix. It will look like this one, right. So, the 4 strain gauges here, these strain gauges you cannot see from this side, okay. That is in the other side of the shaft. So, we cannot see this, that is the reason I have dotted like dotted. So, this will give you the 4 strain gauges. Let us look at that. Yes, you see here that this is our, you see that these strain gauges 3 and 4 you cannot see. This is a 45-degree helix, and you see here this is a 45-degree, this is a 45-degree angle, it is coming up, this is 45-degree, this is also 45-degree helix, this is 45-degree, this is also 45-degree, and these 3 and 4 you cannot see from this side, right. It is on the other side of the, that is the reason we have drawn it different with a different color, right. And so, I should draw here, fine, strain gauges 1 and 2 and 3 and 4, right. Now, let us look at, so this, the installation of the gauge is very important, because it will, if it is not in the helix, we cannot write the actually the equations of this output voltage for the torque cell. Now, 4 strain gauges are mounted on 2 perpendicular 45-degree helixes, as I told you, and the strain gauges 1 and 3 are mounted on the right hand helix, and these are under elongation. Please note, these strain gauges 1 and 3 are mounted on a right hand helix, these are under elongation. Strain gauges 2 and 4 are mounted on the left hand helix, and these are under compression. So, we have seen also in the previous cases, when the 2 strain gauges are elongation and 2 strain gauges are under compression, so we can put an Weierstrass in such a way that our B output will be quite large. If it is not 4 times, it can be quite large, because all the strain gauges are active. You see, the I can measure in all the previous cases also in the lesson, we have seen that we can use a single strain gauges, but we are using multiple strain gauges to maximize the output voltage, right. So, strain gauges 2 and 4 are mounted on the left hand helix, and these are the compressions, and the strain gauges 1 and 3 are mounted on the right hand helix, and these are under elongation. The shearing stress tau on the circular shaft is given by tau equal to Td by 2j, which is equal to 16 pi d cube. This is equation number 1, where T is the applied torque, J is the polar moment of inertia of the circular cross section, and D is the diameter of the shaft, right. If we put all these things, I can get the shear stress, and we assume that all the normal stresses are 0 in these cases. The shaft is in the pure torsion, the normal stresses will be 0. Then for a circular shaft, we can write sigma 1 and sigma 2, sigma 1 minus sigma 2 equal to tau xz. I think this will be equal to, sorry, this will be equal to, so applying Hooke's law, the principal strains epsilon 1 and epsilon 2 are obtained as epsilon 1 equal to 1 by E, sigma 1 minus nu sigma 2 16 T pi d cube 1 plus nu into E, right. And epsilon 2 equal to 1 by E sigma 2 minus nu sigma 1 equal to 16 T by pi d cube 1 plus nu divided by E. However, delta R by R, R equal to lambda. This is actually delta R by R is a change of resistance. So, as you know the definition from the definitions of the gauge factor, because as you know this is the gauge factor is actually defined as delta R by R delta L by L. We have seen this thing, right. So, which will give you, so this is epsilon, this is equal to epsilon. So, I can write that delta R by R equal to lambda into epsilon, is not it. So, observing the installation of the 4 strain gauges, if you look at the installations, because we have seen that the strain gauges 1 and 3 will be under elongation. So, it will sense the positive strain, and strain gauges 2 and 4 under compressions. So, it will sense the negative strain. So, what will happen, you will find that the delta R2 by R2 will be negative with respect to delta R1 by R1. So, we have written the equation delta R1 by R1 equal to minus delta R2 by R2 equal to plus delta R3 by R3 equal to minus delta R4 by R4 equal to 16T pi d cube multiplied by whole 1 plus nu E minus into lambda. So, this is pi, please note it is not in the math mode. So, actually it is pi like this one. Now, the strain gauges are connected in a Wheatstone bridge as shown in the following figure. So, all the strain gauges is, you see this is the strain gauges we have. You see this is connecting the strain gauges in the Wheatstone bridge is very important. So, that suppose in the very common question in the case of link type load cell, that if we, what will happen if you connect if you interchange between R2 and R3. So, that will give you a problem, because in that case what will happen, you see R1 and R3 both will increase, and if I interchange, I am talking about, if I interchange R2 and R3, what will happen, you see in that case both R1 and R3 will be under elongation, R2 and R4 will be under compression, right. So, the unbalanced voltage will not be there. So, this will create problem. So, for that reasons we have connected like this. Therefore, the unbalanced voltage of the Wheatstone bridge can be expressed as, you see here, E naught equal to 16 T by pi d cube into 1 plus nu divided by E lambda into E x. So, what are the legends? You see the legends are very important. I am sorry. This is the sensitivity of the torque cells. So, if I go S equal to E naught by T equal to 16 1 plus nu lambda E x. You see, if you look at these are these excitation voltage of the Wheatstone bridge. This is Young's modulus of elasticity. D is the diameter of the shaft. Nu is the Poisson's ratio of the material of the shaft, and lambda is the gauge factor of the strain gauges, whatever the strain gauge factor you will use. So, you see that this is our sensitivity, that means for unit change of torque how much the output voltage I will get in the Wheatstone bridge. This is the sensitivity of the torque cell and the Wheatstone bridge combination. Now, obviously what you will see, you see that here you can increase the sensitivity by increasing the excitation voltage, by increasing the lambda, that means increasing choosing the type of strain gauges which is higher lambda. But as you know that the lambda is varies little, it varies from 2 to 4 usually for the metal wire gauges. Whether it does not matter, because suppose if you take advanced, it will be lambda equal to 2, if you take isoelastics it will be equal to 3.5, and if you take tungsten, all these things, you will get the lambda equal to 4 point something, 4.1 or something. So, it is not doesn't vary much until unless if you use a semiconductor strain. The semiconductor is not very suitable for this type of operation, because it is in large vibrations and all those things are there. So, I can increase. So, lambda do not have much choice. So, either 2 or 4, and excitation voltage, as I told you earlier also, we cannot increase the excitation voltage because it will increase the dissipation in the individual strain gauges. So, now all the strain gauges has some limitation, that means how much power you can dissipate. Ultimately it is a resistance. So, obviously how much power it can dissipate you must calculate, right. So, depending on that you can optimize the value of the excitation voltage in the Wheatstone bridge. Obviously, if you can reduce the D, obviously the and E, Young's modulus of elasticity, your sensitivity will increase, but reducing D and reducing E obviously will decrease the range of the torque cell, right. Now, see the sensitivity of the range of the torque cell will be given by pi d cube, this is a T max, the maximum value of the torque, pi d cube by S tau by 16, right. So, if you reduce, you see here, if you reduce D, obviously what will happen, that the value of the maximum torque also will be reduced. If you reduce E, at the same time S tau also will reduce. So, obviously T max also will reduce. So, you have to make a compromise between the sensitivity and the range of the torque cell, right. Now, where S tau, which was in the previous equation, is the yield strength of the material, right. Now, voltage ratio at the maximum torque can be given by E naught upon E subscript E x maximum will be expressed as follows: is E naught by E x max equal to S tau lambda 1 plus nu upon E, right. S tau is the yield strength, lambda is the your gauge factor, 1 plus nu, nu usually varies, it is around 0.3, and E is the Young's modulus of elasticity, right. So, it will give you the maximum voltage for a particular value of the excitation. What can be the maximum voltage output for a particular value of the excitation, right. So, we will show you one example by which you will know that how much will be the, suppose for 10 volt power supply, how much will be the value of the E naught, maximum E naught, right. So, here also you can see that if I increase the, decrease the E or decrease the S tau, so obviously what will happen, the maximum voltage also will decrease. Now, we have taken example, if S tau equal to 4.14 10 to the power 8 Newton per meter square, Young's modulus of elasticity, it is 2.068 10 to the power 11 Newton per meter square, where nu is 0.3 is a Poisson's ratio and lambda equal to 2, then E naught equal to E x, I can add maximum equal to 5.2 millivolt per volt, right. So, it will give you the 5.2 millivolt per volt. So, you can say that if you have a 10 volt power supply. So, if I have a 10 volt power supply, so I will get a 52 millivolt maximum output from the load cell. Now, data transmission is most important. It is not very important in the case of the other cell like your link type load cell or the load cell, I am talking about link type load cell or the beam type load cell, because these are stationary. Whereas, in this case you see all the strain gauges power supply, especially strain gauges, is to be rotated at the same speed, because these strain gauges is to be cemented on the shaft, and it is rotating at the same speed as the shaft of the machine. So, it is very much necessary to give the power supply, because whenever you are using in a Wheatstone bridge, you have to give the power excitation voltage to the bridge, as well as you have to take out the unbalanced voltage from the bridge. Whether you are using null balance, it does not matter. So, you have to take out the unbalanced voltage from the bridge. So, there are two methods. One is the slip ring method. Slip ring method is very common, and other is the wireless telemetry system. Now, slip ring method is common because people worked on slip ring for a quite long time, and the telemetry method is rather new in that sense, right. Now, you see here that this is basically a slip ring method of the torque measurement. So, you have the same 3 strain, these are all installed on the torque cell. Please note, these are all 1, 2, 3, 4 are all installed on the strain gauges, on the torque cells with the usual cement and all these things. You must install the gauges, and we have the slip rings. These are the basically slip rings. You can see this is the slip rings. The 4 slip rings are there. So, through this I am giving the excitation voltage. Okay, through this slip rings excitation voltage is there, and through other slip rings, through this wire and slip rings, because this part is rotating and this part is supposed to be stationary. This part should be stationary and this part should be in rotating, right, because it is on the shaft itself. So, through slip rings we have to take out. Now, there is a typical problem with the slip rings, because you see the contact resistance varies, and as I told you, you cannot increase Ex, because that will control the dissipations in the sensor itself. So, you have to limit the value of the X. So, when the contact resistance varies, what will happen? The current will also vary. So, which will lead to the noises in the system. This is one problem with the cases of slip rings. You have to use some special materials, and you have to use some special, some optimum forces you have to apply, so that there is no variation of the no variations of the pressure, or because ultimately it is a brush and spring. So, there is no variations in the pressure. So, all this thing you have to look at, only then you will get the value, the E naught, which is noise free, right. So, this is basically, you can use another slip ring also like this one. So, you can use another one. Okay. So, this should be in contact, actually it should be like this one, right, please note, right. So, this will go like this one. So, I can have all the four, I can have all to reduce the current in each ring, right. If the current is large, so we can usually in the DC machine, all these things we give the power like this. So, same principle is used, same, because we have the some technology we know. So, based on that we have developed these type of systems, right. Now, the slip ring assembly contains insulated rings. Now, the details of the slip ring method. The slip ring assembly contains insulated rings mounted on the shaft and the brushes mounted in a case. The case will remain stationary, since high speed bearings are placed between the shaft and the brushes, right. The drawback, as I told you earlier, the contact resistance between the rings and the brushes vary, that the noise will be developed in the excitation of the bridge and the bridge output, because both the, you see the, when you are taking the, sorry, that we are not taking only the bridge output, even your excitation voltage also will contain noise, right. And there will further noise will be added when you are taking out the unbalanced voltage. That noise will be already present in the unbalanced voltage. Noise present means whatever the noise entering the, even though you are giving a supply from a battery. So, those slip rings will introduce some noise, which is going to the, as excitation to the bridge, and when you are taking out the unbalanced voltage from the bridge also, you will get the noise. It will be added rather. Now, special rings made of the copper nickel alloy and the brushes made of silver graphite mixtures are used to reduce the noises, right. So, the different special types of slip rings you have to use, so that the made of silver graphite and mixtures, which is used to reduce the noises. Now, next is coming the telemetry systems, or that systems which is or a wireless telemetry system, because there is no wire to avoid all this. Because you see, the whenever these type of things are there, slip ring is another problem which you have not discussed. It is prone to very wear and tear after long rotations, after rotation for a few days, when the shaft is rotating continuously in a plant. So, what will happen, that there will be wear and tear, all the brushes will be there is a wear and tear in the brushes. So, you cannot avoid that, but instead if I use a telemetry system, so wireless system which is totally contactless, so that type of things will improve the life of the entire measuring systems. So, I will discuss now the telemetry systems. Telemetry obviously means the wireless telemetry. It utilizes a split collar that fits over the shaft, right. There is a split collar which fits over the shaft, and a power supply to bridge, a modulator, a VCO means voltage controlled oscillator, and antenna are placed on the split collar. So, what are the placed is a power supply to the bridge, a modulator, a VCO, and antenna are placed on the split collar. The unbalanced voltage is passed through a PWM pulse width modulator that modulate a constant amplitude 5 kilohertz square wave. You see this is a 5 kilohertz square wave. Okay. Now, what is this actually? You see that unbalanced voltage is coming. Let us look at some of the you see what will happen. So, there are different modulation techniques, as you know, that we have a pulse width modulations, you have binary phase shift modulation. So, this is one of the modulation techniques. Suppose I have the signal here, sorry. Isn't it? This is a wave, okay, and we can have another wave of like this. Yes, or we can have another wave right, is not it. You see here in all the three cases the average value will not remain same. In this case average value will come down here somewhere like here if I take a different pens. So, average value will God knows, yes, average value will come down here, you see here. In this case average value will come down here, and in this case average value will come down here. Is not it? I do not know, it might be not very much visible. So, I can take some other pen. You see the average value is changing in all the three cases, is not it? However, you see this is the time period of your signal. If I take this is the time period of your signal t. You see the t remains constant, right. So, what is varying then? If you carefully note, in communication systems we call it mark. In a wave this is called mark and this is called space, right. This mark to space ratio is getting changed, right. If mark to space ratio is 1, we call it 50% duty cycle clock, right. If the mark ratio is not 1, so we will call something else, not the 50% duty cycle. M is mark and this is space, right. Now, here you will see that mark to space ratio is 1. Now, in the case this is the case 1. In case 2 we made m by s greater than 1, that is an average is going up, right. And in case 3 you look at very carefully, m by s is less than 1. All the cases you see, I am sorry, this cannot be the your fine, right. So, actually time period will come where? It will come down here. Oh sorry, this should go away. How it will go? Okay. I am sorry. So, it will come like this. Now, see one thing very important, that here I mean you will see there, let me choose the pen again. Here that Mach to space ratio is varying. If the Mach to space ratio varies, then what will happen? Obviously, you will find that the average value of your signal also will vary. This signal, this average value of the signal be fed to a VCO. Now, VCO, as you know, is a voltage control oscillator, is nothing but the input is a DC voltage and the output will be the frequency, and which are varying frequency. So, depending on your input voltage, your output frequency will vary. This is typically a VCO or voltage control oscillator. It has always a free running frequency, right? Usually it is by quite high. So, we can make a free running frequency, suppose 10.7 megahertz or something like that, right? And along with that we can do that thing, right. So, this is actually, so if I choose this one, so it will look like this one, right. This is our time period, this is actually the time period. You see the time period is not varying in all the cases. You see if I take this one, so time period is not varying, right. So, this again time, this is the time period here, is not it, but the Mach to space ratio is getting it, that is actually the PWM, pulse width modulators. I am modulating the width of the pulse, by which my signal will be, because you see the DC signals which I am getting, that is a very low value. So, we cannot transmit it, I mean a DC signal cannot be transmitted, it is to be converted to AC signal. That is the reason we are making it pulse width modulated. Once we got the pulse width modulations, we now again we give it to the, again we are taking some DC signal here, then we are giving it to the some voltage control oscillator, right. So, it utilizes the split collars which I was discussing, and amplitude of unbalanced voltage is passed through as PWM that modulate a constant amplitude 5 kilohertz square wave. So, the basic square wave is a 5 kilo. That means what is that? That means what we are discussing. That means if I take a, so this signal, so this is T, so F equal to 1 by T equal to 5 kilohertz, right. Now, if I go back, now square wave will vary the frequency of 10 megahertz of the VCO, right, because square wave actually we cannot give, we will smoothen it, we will convert it to DC, and then it will convert, like what will happen, you see here that actually if I look at, so we have the unbalanced voltage which is coming from the strain gauge, or I should say it is a Wheatstone bridge. So, it looks like this, that is I have a Wheatstone bridge. Then it is coming to the, this is a DC voltage, this is a DC voltage, it is coming to a PWM, then we are coming to a low pass filter, because you see this signal which is coming from the PWM, depending on the, this is to be convert to the pass through low pass filter to average it, okay. Our signal can be like this, okay, like anything. Then it is coming to a VCO. Now, here this the frequency which we are modulating, it is 5 kilohertz. What is 5 kilohertz? That means this frequency, that means if I say the time period, so T or F equal to 1 by T equal to 5 kilohertz. Whereas VCO frequency is quite high, is around 10 megahertz or something like that, right. So that this will control over this one, that means some DC voltage will come down here, which is giving to the output. So the output voltage of the VCO will be proportional to the DC voltage we will give, and this DC voltage again will depend on the unbalanced voltage of the Wheatstone bridge. Clear? Now, the square wave will vary the frequency 10 megahertz of the VCO. The VCO signal is transmitted through the rotating antenna. Everything is rotating. I mean, VCO signal is transmitted through the rotating antenna, and the signal is received by stationary loop antenna that encircles the split collar. Okay. It is a collar like this one. So, if you look at it, it's very difficult. So, we have a shaft and it is a split like this one. So, it will put like this one. Okay, split, we can split it. So, there is another antenna here on the outside and it is stationary. Inside is rotating, there is another antenna in the rotating shaft also, right. Now, how I will give the power supply to the bridge next, that is. So, signal is received by stationary loop antenna that encircles the split collar. So, there are two antennas. One is rotating antenna, which is installed in the shaft itself, and that antenna is rotating at the same speed as the shaft. So, antenna, your Wheatstone bridge, power supply, everything is rotating, and stationary loop antenna. The signal received by the stationary loop antenna. Interestingly, you see that the same stationary loop antenna can be given for both the excitation given to the bridge as well as taking out the unbalanced voltage. Obviously, the frequency will be different. So, there is no question of overlapping. We can, at the receiving end, we can have band pass filter. The power supply to the bridge, you see here, power supply to the bridge, PWM, pulse width modulator, and the VCO, because we are assuming that the low pass filter is incorporated within the pulse width modulator, and the VCO is fed through inductive coupling by a 100 to 150 kilohertz signal transmitted by the stationary loop antenna. Okay. There is no battery we are providing as such, because Wheatstone bridge needs some excitation, is not it. So, that entire all the cheap excitation, all the everything we are giving through a stationary loop antenna, which has a frequency of 100 and 150 kilohertz, and other frequency, the VCO frequency, it is quite high, it is 10 megahertz. So, if you are at the receiving end on the, if you have two different band pass filters of the appropriate bandwidth, okay, we can easily separate these two signal. Or if at the receiving end, if you have a low pass filter, obviously this signal will go out, that means excitation signal will go out, we will receive only the signals which is coming out of the bridge, which is very high frequency, around we have a 10 megahertz is a frequency. So, around 10 megahertz, because when depending on that, you see it's what will happen, you see here that I have a 10 megahertz signal. Okay. So, over this there is overlapping. So, I will get a signal range like this. So, this is 10 megahertz. So, this is minus delta F, this is plus delta F, I will get. So, over this, depending on the unbalanced voltage of the Wheatstone bridge, I will get, this is the center frequency of our VCO. This is a VCO center frequency, right. So, this 10 megahertz signal, so over this I am getting shift, right. So, on both sides you will get a signal of depending on the whatever, and this how much the shift will be, because since it depends on the DC voltage, input to the VCO is the DC voltage, how much is the shift will also depend on the Mach 2 space ratio of the PWM, and the Mach 2 space ratio of the PWM will depend on the unbalanced voltage of the your Wheatstone bridge. So, the frequency shift around 10 megahertz of the VCO will depend ultimately on the signal which is coming from the unbalanced voltage, right. Now, interestingly, you see the usually how much this will, suppose this is 10.5 megahertz, a unbalanced voltage, a frequency of the VCO corresponds to unbalanced voltage, and what is the frequency of the which is giving to the stationary antenna, suppose 150 kilohertz. So, these two frequencies are totally different, we can easily filter out this analog two frequency, we can filter out by a low pass filter. If I use a high pass filter, obviously, so this frequency will get and this frequency will be chopped out, clear, because our information about the unbalanced voltage, because this unbalanced voltage or the shift of the frequency from the VCO center frequency will be calibrated in terms of torque, please note that. So, this frequency will be calibrated, this is the shift of frequency will be calibrated in terms of torque. Ultimately, if the larger torque, the frequency shift should be large, if the smaller torque, frequency shift will be small, around 10 megahertz, right. So, this frequency change is to be calibrated in terms of the torque, and if I get this signal by a high pass filter, simply if I can reduce the, I can chop off this 150 kilohertz signal. So, I will get a 10.5 gigahertz around that thing, fine, no problem. So, I will get that signal, I will calibrate my meter according to the torque, right. So, this is all about the power supply, all these things. And this almost we came to the end of this lesson. Before we are going to the some exercises, I will give you the exercise and I will give you the solution also, but please note I will give the answer but not the solution as such. So, you should compute of yourself. This is nothing but plugging in your all the expressions and you will get the answer. This is nothing a great deal, but to know that what is the typical range and all these things, just to glimpse of the flavor of the what is the torque measurements, what is the typical range and all these things. You see here, let me take a blank page. The problem is like this. Problem 1. Determine the sensitivity of a torque cell if modulus of elasticity of the link material E, which is the modulus of elasticity of the link material, is 2.0684 into 10 to the power 11 Newton per meter square. Then Poisson's ratio mu of the link material is 0.3. Excitation voltage, that means EEX is equal to 8 volt. Diameter of the shaft D is equal to 2.54 centimeter, right. The gauge factor of the strain gauge lambda is equal to 2. This is advanced strain gauge obviously, and the resistance of the gauge, resistance all are active gauge, resistance of strain gauge is equal to 120 ohm. Okay, so it is nothing, I mean to just to plug in all this formula. So it is 10 to the power 11, please note 2.0684 in 10 to the power 11, right. So you plug in all this value, you will get the sensitivity, because we have already given the expression for the sensitivity in our class, right. So answer you will get, I will give you the answer you will get is 3 point, just plug in all those values, 125. In which equations you have to play, because what I ask you to find the sensitivity. So if I look at, so that if I have the sensitivity expressions, you see our sensitivity expressions looks like this: S equal to E naught by T equal to 16 1 plus nu lambda Ex pi d cube E. All data are given, is not it? So in what sense? You see here E is given, E is 2.0684 into 10 to the power 11, Ex is 8 volt, this is 8 volt, this is 2.0684 into 10 to the power 11, D is given, although it is given in centimeter, it has to be converted in the meter. So, it will be 0.0254 meter. Then Poisson's ratio is 0.3, lambda is 2. So, if you calculate, so actually the value of S will come up as S equal to 3.125 into 10 to the power minus 5 volt per Newton meter, right? Voltage by torque. So, obviously it will come like this. Now, interestingly, the second part is telling the let me write the second part. The sensitivity of torque cell can be increased if input voltage or excitation is increased, right? That we have seen, is not it? We have seen that if we increase the excitation voltage, our sensitivity also is increased, because sensitivity expressions we have seen that it is in the numerator, is not it? All the sensitivity informations we have seen, the sensitivity expressions, it is in the numerator, is not it? Because sensitivity, if you look at, it is this 16 plus nu lambda Ex upon pi dq, is not it? So, if I increase Ex, obviously my sensitivity will increase, right? Voltage Ex is increased, so that is given as it is. So, that means if I take this one, is increased if each gauge can dissipate, each gauge means each strain gauge is dissipate 0.8 watt of power, determine the maximum sensitivity that can be achieved without damaging the strain gauge. You see, always there is a strain gauge has some limitation, that means how much power it can withstand. So, that is already given 0.8 watt of power it can pass. So, accordingly you must calculate the current. Once you get the current, you know the voltage. So, once you get the voltage, you can calculate the sensitivity, right. So, the sensitivity here in this case will be S equal to S max will be given by 7.5 into 10 to the power minus 5 volt per Newton meter, right. So, with this I came to the end of this lesson, that is of torque cell. Welcome to the lesson 7 of industrial instrumentation. In this lesson, basically we will discuss the thermistor. As you know, the thermistor is a temperature sensitive device. I mean, if you increase the temperature, its resistance decreases, and by using this property, mainly it is used as a temperature sensor, but it has many other applications in electronic circuits that we will discuss one by one. Now, contents of this lesson is its resistance temperature relationship or characteristics, composition of a thermistor, because it is a semiconductor material. So, you have to look at what are the compositions and how it is made, manufacturing process, how actually thermistor is made, and thermistor in a Wheatstone bridge. This is very important. We will show that Wheatstone bridge is used to take an unbalanced voltage which is calibrated in terms of temperature, and its linearity of operations. We will also see the thermistors in a potentiometer circuit. Either you can use it in a Wheatstone bridge or in a potentiometer circuit. We will see both, we will analyze both. And what is the linearity of operation? Thermistor is a very non-linear sensor. So, we will look at all these things. A thermistor also can be used in a potentiometer circuit, right? You see there are various potentiometer circuit used in the potentiometer circuit as follows. You see this is one of the thermistors which is used in a potentiometer circuit, right? You see here that this should be the sign. So, this is the thermistor RT and R1. In this case, if RT equal to R1, so RT dash will be equal to RT, that means change resistance, where RT dash, as I told you earlier, equal to RT plus delta RT. RT dash equal to RT 1 minus 2 E naught by Ex, excitation, upon 1 plus 2 E naught by Ex. Now, interestingly, one common question arises, what will happen if I flip it? That means, if I put RT here and R1 here, that means the circuit, if the circuit looks like this, then what will happen? This ends the lesson 7 of industrial instrumentation.